Well, good morning, everyone. We met last week. My name's Bradley. I'm one of the engineers at the MathWorks Australia office. Look, the good news for this morning session is most of the setup work that we need done today, we actually did last week. So let me just sort of walk through that. The first step that you had to do was just download the zip file that contains all of the MATLAB and Simulink example files that we'll be using today. We did this last week. I'm assuming that you've still got that zip file. The second thing that we're going to sort of do straight away is I'm just going to get you to launch your MATLAB installation. So preferably that's the R2023B, or if you happen to have the latest and greatest R2024A, that would be good too. So look, I'm just going to launch MATLAB R2023B. So if you're following along at home, double click on that MATLAB icon. I'll ask for a show of hands in just a moment, just to make sure that we're all on the same page. But once the MATLAB desktop appears, something that I really want you to sort of pay attention to is you'll get some feedback on what your present working directory is. I'm going to refer to this as the present working directory folder breadcrumb. And you can sort of interact with these sort of inserted drop-down boxes to sort of navigate to the folders that you want to go into. So I'm going to use this present working directory breadcrumb folder trail to navigate to where I put the zip file. Yeah. So I'm just going to, right from the get-go, go to my C drive, and I think it was in a folder called BH, and I can kind of see it. It was in a folder called Today. So just want you to sort of navigate to wherever that folder was that you had your zip file. And the next step is optional. Remember, we did this last week, so there's no point in redoing it if you've already done it. But for the sake of completeness, the next step is to simply unpack that zip file using MATLAB's command window. So if you sort of click on MATLAB's command window and just type in the command unzip, you'll need to supply one input argument, which should be the name of your zip file. I don't know exactly what the name of your zip file is. I'm sure you do, though. So whatever that is, just type that in, hit enter, and it should unpack the zip file. So folks, this is a go no go point. I'm looking at the chat box. Is everyone sort of up to date? Remember, we did this during last week's session. So if you are ready to go, can you just type in the chat box ready to go? And that'll just give me some feedback as to whether or not we can proceed. All right, thanks, Tim. Thanks, Matthew, Dan, Andrew, Fergus. So I'm counting seven ready to goes out of, not counting myself and Dongbin, 18. So we're not even at the halfway mark yet.
Yeah.
So I'll just wait maybe another minute or so until you've been able to get yourself to this position. And when you have, just type into the chat, ready to go.
Leon is asking where you can get the link for the zip file. I'm trying to copy that from Canvas.
All right, so we're running at 9 people out of 18 are ready to go. That's half the class. That's not bad. So Dongbin, should we maybe wait another minute or so, or should we proceed?
Now look, 20 students here, no, 18 students here. Okay, so I think we should be good to go.
Okay. All right. So you've unpacked the zip file, and it's simply unpacked a folder, which I'm going to navigate into right now. I'm just going to sort of double click on that folder. And when you navigate into the extracted folder, you should see these four subfolders. So last week we did this one, and we did the spool on the truck bed. So this week we'll be covering the virtual lab on a pendulum impacting a block, and we'll also be looking at a suspended pipe pendulum. So the first problem that we're sort of going to look at today is the pipe pendulum case study. So that would be this guy. So if you can, just double click on that folder, pipe pendulum. When you've done that, a go, no go point for yourself is just have a look at that present working directory breadcrumb trail and just confirm that the very last folder that's mentioned is pipe_pendulum. If you see that, then you are ready to go. If you do not see that, you are not ready to go, and you need to go back and try and navigate into this folder. All righty. So look, before we sort of fire up, let me just sort of outline why we're doing the things we're doing this morning. So all I want to sort of get out of this session with you today is just to make sure that you're comfortable opening the case study files, modifying the case study files, and running the case study files, right? And the reason that that's important to you is my understanding is that for your final semester project, that's what you're being asked to also do. Just to visit these case studies, make some parameter changes, run the models, and do other things. All right, so I'm hoping that we're all in the pipe pendulum folder. So let's open up. Again, just so that your screen looks roughly the same as my screen. If you haven't already done this, just go to MATLAB's folder panel, the one that I've clicked on at the moment. When you do, just sort of click on that little round icon that's up in the upper right-hand corner. It'll bring down a context menu. When it does, just choose group by and then type. And this will simply force the folder panel to display all files with the same file extension. So all of the MATLAB script files are grouped together, all of the Simulink files are grouped together. Just makes it easier to find stuff. All righty. So if you've done that, you'll probably notice that there are 4 scripts, tasks. So tasks 1, 2, 3, and 4. So let's start obviously with task 1. Let's get you to double click on this file, and let's have a look at the task 1 script file. So just double click on that guy to open it. Alrighty. So look, let's talk about the case study that we're going to look at. So this is the system that we're going to be kicking around for the next sort of 40 minutes. It's a really simple pendulum, albeit an engineering sort of application of the pendulum. I think that the case study that you've been given sets the scene that you have a forklift that has a concrete pipe suspended over the 2 tines of the forklift. So we're going to sort of idealize that situation by just looking at a pendulum, all right? So the pendulum is made up of a circular tube, a pipe, right? That pipe has a mass, and it has a moment of inertia about the center of mass. And we're going to sort of assume that although there is this sort of additional sort of strap length, that this yellow length is its mass and inertia can be ignored. All of the mass and inertia is effectively at the concrete pipe. So it's a 1 degree of freedom system. If you know the angle theta, then you're able to sort of position this pipe into any pose that's permitted by the constraints of the problem. So we have a concrete pipe pendulum. Let's play with it and see what we can do. So the very first thing that we're going to do is we're actually going to derive the equations of motion using Newton's second law. And although this is a relatively straightforward problem that you could easily do with pen and paper, I'm going to sort of show you how MATLAB can do symbolic computing. And symbolic computing is really nice for when the systems that you're studying, the expressions that you're having to write down are starting to really grow and grow and grow. Symbolic computing won't think for you. It doesn't know engineering. But if you as the engineer know what it is that you want to do, then you can ask symbolic computing to do those things, without having to write out pages and pages of derivations. So the very first thing that we're going to sort of do is we're going to sort of declare some symbolic variables. And hopefully these symbolic variables look very familiar. We've got the length of the yellow rod that connects the pipe pendulum to our pivot point. We've got the radius of the concrete pipe, its inertia about its center of mass, gravity, mass. We've got a bunch of other variables that define the angular position, velocity, and acceleration. As you'll see in a moment, when we draw the free body diagram, we'll also have to represent the reaction forces at the pivot point. So let's get ahead of that and define some symbols that represent those reaction forces. So the very first thing that we're going to do in this script is you're going to walk up to this script section called Define Symbolic Variables, and you're just going to click anywhere. Again, just going over some of the MATLAB script navigation sort of steps. I just want you to click anywhere inside this section, anywhere at all. And when you do, you should notice over on the left-hand side that you get this sort of blue strip. And that gives you some visual feedback that this is the currently selected section. Not only does it give you that feedback, but if you click on that blue strip, it will execute just the MATLAB code that is defined in this section. So I'd like you to do that right now. Click on that blue strip and it will execute the MATLAB code of the currently selected section. So let me just sort of do that now. So just to confirm that it really did do that, if I have a look at the contents of my MATLAB workspace, you can kind of see that it's got all of those symbolic variables that were defined in that section that we just executed. So yeah, again, if you don't see this, you haven't followed that step correctly. So have another go at doing that. Alrighty. Now, as mentioned in the intro, we're going to utilize Newton's second law. F equals sum of the forces equals mass times acceleration. So let's get ahead of that right now, and let's compute the acceleration vector of the concrete pipe. Yeah. So if you sort of have a look at this, just this schematic, note the geometry. L plus R cos theta is the vertical y coordinate of the pipe. L plus R sine theta is the horizontal coordinate of the pipe. So if you sort of take that information and you just define what the position vector of the center of mass of the pipe is, so you'll write that out. And then we can kind of utilize MATLAB symbolic computing library and compute the symbolic derivative of that position vector. We'll do it twice, right? We'll get the velocity vector and the acceleration vector. So just click anywhere in this section. So again, click anywhere in this section. Observe that you've got your blue stripe, and then click on that blue stripe. So when you do that, in fact, you know what? I'm going to sort of change the display mode of my script just so that I can utilize as much of the screen as possible. If you want to follow at home, you're welcome to do so. So I'm just going to click on this display icon on the upper right-hand corner, and it will now change the display of the MATLAB script. So just click on that icon. That's better. So the significance of making that change is that now in the script, whenever we sort of echo results, you will see the results being displayed immediately below the line of code that produced that display command. So I guess what I'm sort of lighting up in this sort of red balloon right now is this is the X and Y components of the pipe pendulum's center of mass acceleration. Yep. So XG double dot and YG double dot. All right, so this has got us in a good place, ready to apply Newton's second law. So before we do that, your engineering sort of training kicks in, and you're going to draw that free body diagram. It's a really simple system, so there's not much to draw. You isolate the rigid body, and it of course has the mass force, mg, and at the pivot point, it has the reaction forces exerted by ground onto the actual yellow rod. So we've got a horizontal reaction force and a vertical reaction force. So from this free body diagram, let's go nuts and apply Newton's second law. So if you were to write the Newton's second law for the horizontal component of forces, it's mxg double dot equals rx. So that was pretty straightforward. If you were to do that for the horizontal forces, it's myg double dot is the difference between your reaction force and your weight force. So the really nice thing is that the implementation of those two equations in symbolic math form, it's almost exactly the same as you write it out, right? So lines 15 and 16 sort of show us writing out those two equations in symbolic form. So note that we're utilizing the accelerations that we just computed in the previous section, all right? It's a vector. The first component of the vector is the x acceleration. The second component of the vector is the y acceleration. So we've got these two symbolic equations. There is, of course, a third equation that we could write, right? And that's the sum of the moments about the center of mass of the pipe pendulum. So there's clearly the center of mass of the pipe pendulum. This is the angular form of Newton's second law. And now just, again, studying the free body diagram along with this little geometry aid, I'm sure that you can convince yourself that this is the sum of all of the moments that are acting about that center of mass. So again, let's click in this section, all right, and then move across to the left and just execute it by clicking on your blue bar. All right, so let's scroll down to the next section, pause and ponder. And I want you to just right from the get-go, let's just execute this. It'll just echo the three equations that we've created, and then we can talk to it. So just click in this section and then execute it by clicking on the blue strip on the left-hand side. So here are our three equations. And I guess you're probably wondering, hey, for a single degree of freedom system, why do we have three? Why do we need three equations? Well, one approach is to say, well, two of these equations incorporate the constraints of the system. So you can sort of substitute in what you know about Rx into maybe here. You can rearrange the second equation to get Ry on its own, and then you can substitute that into there. And if you go through that substitution dance, then yes, you will only have one equation that completely describes the system. But you know what? Given that we're taking a computational thinking approach to this, we're already started using symbolic computing. We're going to stick with our three equations, right? Because those three equations happen to have three unknowns. So they have an unknown of theta double dot, and the two other unknowns are our reaction forces, right? In a lot of engineering design problems, ultimately you want to know what the reaction forces are so that you can sort of do a stress analysis around that attachment point. So it's not like, we're wasting our time computing our Rx and our Y. So folks, we've got three equations with three unknowns. And if you have a real close look at our three equations, all three of our knowns are linear, right? So theta double dot always appears on its own. You'll never see theta double dot squared. You don't see cos of theta double dot. So it's always theta double dot times something. And similarly, the reaction forces also appear as linear. So the significance of making that statement is we have three equations that are linear in terms of our unknowns. So are you thinking what I'm thinking? I bet you are. So we can solve a system of three linear equations with three unknowns. So what we're sort of going to do is we're actually going to rearrange our three equations into this classic form. It'll produce an A matrix, a B matrix, and our unknown vector x is the vector that contains our three unknowns. So let's use symbolic computing to rearrange those three equations into this A times x equals B form. So if I sort of scroll down to the next section, this is where we actually do that. So if you can click in the section called Let's Solve for Our Unknowns, click on the section and then execute it by clicking the blue strip on the left. So line 22 is simply invoking the equations to matrix function, which does the rearrangement of our three equations, subject to what we've told it is our unknown vector x. It's given us our coefficient matrices A and B. So from here, it's really simple to sort of solve for the unknown x. I'm guessing those of you that did Professor Zarowski's MATLAB programming class a little while ago, you're probably familiar that in MATLAB, you can solve this shape problem, A times x equals B, by using the backslash operator. And that will solve for x. So when you do that, here's what the three unknowns look like. Yep. So we've got this guy is our expression for theta double dot, right? Nice, short and sweet. And the two much longer expressions are the expressions for reaction force R of x and reaction force R of y. Alrighty. So we've done it, folks. We've actually done it. We've derived by applying Newton's second law the equations of motion for this system, and we've done a little bit of symbolic rearrangement, and we've solved for the things of interest, right? So we now have symbolic expressions for theta double dot, Rx, and Ry. So in just a moment, we're going to open up a Simulink model that will contain these expressions. Here's how you really quickly convert a symbolic expression into a Simulink block. So there is a MATLAB function called MATLAB function block, and you provide it your symbolic expressions, and then it will automatically convert those symbolic expressions into a Simulink block. Let's have a look at that. So just click anywhere in this section called Convert to a Simulink block, and then click on that blue execution strip on the left. Now, if this is the very first time that that you've either opened a Simulink model today, it's probably going to take a good 30 seconds, maybe even a minute. So I'm just going to sort of wait until you've all got to the stage where this Simulink model has appeared that contains this solitary little yellow block. So once this has happened for you, if you can just type into the chat, yellow block, just type that into chat, just so that I've got a feel for how we're all traveling. All right, thanks, Lachlan. Thanks, Young. Thanks, Anthony. That's 3 down. Thanks, Dan. Tim. Fergus, thank you. So that's 6 of you. And there's approximately 19 students on the call at the moment. So again, I will just wait. Oh, Andrew, yours sounds interesting. I'm getting error messages. Really? So look, I'll take a stab at why you might be getting an error message. Did you install all of the products associated with the UTS license? Or did you maybe only install MATLAB and maybe Simulink? So that's an interesting question for you to get an answer to. And the second sort of question that I'd ask you to sort of think about is, are you definitely in this folder? So the significance of the first question is, in order to complete the example case studies this morning, you'll need a whole bunch of products installed. MATLAB and Simulink are only 2 of them, but there's a list of other products that are necessary. All right, so look, the last sort of response that I'll give to you, Andrew, just to sort of hopefully sort of give you something to work on, is that if you go to your MATLAB command window and type in VER, really short command, VER, and hit enter, it's going to sort of echo all of the products that you've got installed. And if you've installed all of them, there's around about 120 of them, something like that. It's ridiculous. So if you don't have a long list of products like this, yeah, you'll need to go back and install everything. Alrighty, so folks, I think we've still only got around about 1, 2, 3, 4, 5, 6. We've got 6 out of 19 people that have got the yellow block on their screen. So that's it's a bit of a concern. Let me maybe wait 1 more minute, and then we'll move on. Hey, Dongbin, just a bit of feedback. I mean, what would be your advice in terms of waiting and moving on? I mean, it looks like we've only got 6 out of 19 students at this point at the moment, which is about 1/3 of the class.
Yeah. Okay. Can anybody tell me if you like us to hold for 1 more minute? Okay, I think it's okay to go.
All right.
Yeah, thank you.
All right. So folks, if you're kind of curious, this little yellow block, it actually contains our expressions that we just developed in that MATLAB script. And hopefully it kind of looks familiar to you. The block receives some in time invariant sort of signals. What is the inertia of the concrete pipe about its center of mass? What's the length of the yellow rod? G is gravity, M is mass of the pipe, R is the radius of the pipe. But you can also see the last 2 inputs are the time varying signals for theta and the time varying signals for theta dot. So these are the system inputs for the block. And hopefully, as the outputs names indicate, the first output that the block spits out is theta double dot. The second is our Rx, and our third is Ry. So these are the 2 reaction forces acting at the pivot point. If you kind of just double click on that little yellow block, you'll actually see the underlying MATLAB code, right? So this function really was generated today on the 7th of May, now at roughly 9:26 a.m. So this was automatically generated. So the reason this should get you really excited is it doesn't matter how lengthy or how long your symbolic expressions are. They may literally take up half a page to write down, or even tens of pages to write down. It doesn't matter. This mechanism works for short, and lengthy symbolic expressions. All right, so it's nice to know that if you've got a symbolic expression, you can automatically convert it into something useful. So look, ordinarily I'd keep this this window open and then I'd copy and paste this little yellow block into our next model. But the next model that we look at is pre-cooked. So I just want you to sort of take it on faith that we have already copied this little yellow block into the next model that we're about to look at. Okay. So you can close this this Simulink file. Just close it out. We don't need it. We're not going to use it. Just close it. All right. So folks, this first script that we've just been looking at was all about developing from first principles the kinetic equation of motion for this pipe pendulum. What we're going to do next is we're actually going to take that that derived system and we're going to simulate it. We're going to numerically solve it. So if you can just scroll down to the bottom of the script that we've just been looking at, you'll see that it has a section called Next Steps. And I just want you to sort of just click on this link that says Task 2 Simulation. Alrighty, so this is our second task. And we're going to simulate the model. So let's just have a little bit of a looky-loo at what is in this task 2 script. And as I sort of just scroll down it, you can kind of see that that this script is all about sort of defining MATLAB workspace variables that contain numeric values for those quantities that up until now we've been treating as symbolic. So for example, in the simulation that we're about to perform, the length of that yellow rod that connects the pivot point to the pendulum, that yellow rod is 0.25 meters long. The radius of the concrete pipe is 0.15 meters. The mass of the concrete pipe is 700 kilograms. All right, so I just want you to sort of click in this section. All right, define parameters, values for your model, and then just execute the code by clicking on your blue strip. Just before we move on to the next section, besides defining the geometry and inertia parameters for this system, we've also defined the initial conditions for our degree of freedom. So in the simulation that we're about to sort of perform, the pendulum will be at a 30-degree angle to the vertical, right? The angular velocity of the pendulum will be 0. So it's as if a giant grabbed onto the pendulum, moved it, held it steady, and then let go of the pendulum, right? So these are the initial conditions of our dynamic system. So to scroll down to the next section of this script and click it, and then execute the code, right? Alrighty, so we've now got MATLAB workspace variables that contain the numerical quantities for the system that we want to consider. So the only thing left for us to do right now is to now open the Simulink file that we're going to simulate. Let's just scroll down to the section called Simulink file. And look, we've tried to make it really easy for you. There should be a push button on line 19. Just click on this push button. And this should open for you a pre-cooked Simulink file. Alrighty. So folks, let me just give you just another half minute just to make sure that, I know sometimes Simulink does take a little while to start. this is the Simulink file that I'm hoping is opening on your laptops right now. All right, let's talk. So in this Simulink file, we have incorporated two implementations of our concrete pipe model: the yellow implementation and the green implementation. The yellow implementation is our Newton derivation. So let me sort of take you into that system. Oh, actually, before I do, just a reminder of what we talked about last week. Here are three keyboard shortcuts for navigating a Simulink file. If you notice that the blocks in the Simulink file are really sort of small, you can zoom into that system by holding down your control key and then hitting the plus key. And each time you do that, it will just zoom in. Yeah. And similarly, if you do find that you've opened a Simulink model and you've got your face pressed to the glass, so to speak, the shortcut keys for zooming out are Control and minus. And the last shortcut, which is the one that gets you out of jail 90% of the time, is just click anywhere white on your modeling canvas and then hit the space bar. If you're using a MacBook, a Mac, replace the Control key with the clover key. Alrighty, so where were we? We're saying that this Simulink file, it has two implementations of the concrete pipe pendulum: the yellow one, which is our Newton derivation, and the green one, which is our SimScape model. Let's talk to each of these one at a time. So in the model that just opened for you, you should see some tab sheets that are going to help you navigate into the layers of this Simulink file. So the first thing that I'd like to do is just click on that tab sheet called the Brain Newton Model. And yes, that's going to open up the contents of this yellow block. I'm going to hit the space bar just to make sure everything fits on the screen. And I want you to imagine that 10 minutes ago, that little yellow block that appeared, that we've copied that little yellow block and we've pasted it right here. So here's that little yellow block that contains that derivation that we developed about 15 minutes ago. You'll see that it outputs theta double dot, it outputs our reaction force Rx and Ry. Now, a really easy way of understanding these Simulink models, especially when they're being used to represent dynamic systems, is you always start with the integrator blocks. Yep. So the dynamics of our system involve a second order ODE. In particular, we're calculating theta double dot. Yeah, so theta double dot. So you're going to need two integrators, right? Because it's a second order derivative term. So let's pass theta dot through our first integrator, right? You all know what happens then. We get theta dot coming out of it. And then let's take that theta dot signal and let's pass that through the second integrator, and you'll get theta as the output of that integrator. And note, for each of these integration actions, we always have an initial value for the signal that's coming out of it. Yep. That's where those initial conditions come into play. And you'll see that it looks like we've got a little bit of implicit feedback. And what I mean by that is we're taking this time varying theta signal, I'm taking it, and then I'm feeding it back into my block. Yep. And similar for theta dot. So this is how you implement a system of ordinary differential equations in Simulink. Yeah. In order to be able to do this, though, you needed to have some engineering sort of skills. You needed to be able to derive the mathematical description of the pipe pendulum. Yeah. which brings us to the alternate way of modeling. So let me go back to the root level of the model. So to do that, I'm just going to click on this tab sheet. So in the commercial world, it shouldn't be a surprise that because the systems that industry work on are so complicated, you aren't always going to get away with a first principles approach to deriving the underlying mathematics. That's why computer scientists and software engineers have developed really nice computer-aided engineering tools. So as the complexity of the systems grows, you'll more and more start to leverage computer-aided engineering sort of tools. So that green block that's on the screen right now is an example of an alternate way of modeling the pipe pendulum. It uses something called Simscape, which is our primary computer-aided engineering tool for Simulink. So let's have a look what's inside that green sort of system. And you can do that by just clicking this tab sheet called Simscape Model. And again, if things look don't look very pleasant, just hit the space bar. So remember, folks, this is an alternate way of representing the concrete pendulum. There are no differential equations that needed to be created in order to do this. Instead, Simscape gives you a block library that allows you to represent at a very high level the relevant components of your problem. So for instance, we have a block here that allows us to represent the rigid pipe of the system. Similarly, we have a block here that represents our essentially massless rod that connects the pipe to the pivot point. The pivot point is represented by a revolute joint connected to mechanical ground, which is where that must be inside this guy. But anyway, this is that alternate way of modeling. Yeah. So let's go back to the root level and let's run this simulation. Right, let's just see what happens. So if you click on this green run button, yep, this will invoke Simulink's numeric solvers, and Simulink now will numerically solve this system. And when it does that, hopefully this figure again automatically appears on your screen. So this is something called the Mechanics Explorer. And this figure appears when you have Simscape multi-body blocks in a Simulink file, and we do. It's a really nice sort of animation, and it gives you that sort of CAD-like visualization of the motion of the machine. So you've got some nice little playback sort of buttons at the bottom of the figure. All right, but yeah, this is what I would expect to sort of see for this sort of problem. Now, folks, I'm putting it out there. We've got two different ways of modeling this, the yellow model, the green model. Aren't you really curious to know whether or not those two different modeling approaches produce similar results? Aren't you just dying to know that? Well, let's find out. So you can kind of see that we're sort of taking the responses from our yellow model, we're taking the responses from our green model, and then we're going to sort of overlay those two responses and compare them. So let's have a look inside the system called compare. So just click on this tab sheet, compare. And you can clearly see that I need to do the spacebar trick to have all of the blocks properly displayed on the screen. So please click your spacebar, hit your spacebar key. That's better. And now let's bring up some oscilloscope traces of our yellow model response and our green model response. So to do that, double click on this pink oscilloscope block. So double tap on that guy. Alrighty. So in all of these axes that have just appeared, time is on the horizontal axis. All right. So what have we got? The the three axes on the left-hand side show theta double dot, theta dot, and the bottom one is theta. And over on the right-hand side, these two axes, hopefully the labels are pretty obvious, but these show the time-varying reaction forces Rx and Ry. So this is what you're looking at. So if I click on this little magnifying glass, let's zoom in. I'll click on the magnifying glass first, and then I'm just going to just pick any one of these time traces, and I'm just going to start to zoom in until I can really see with my own eyes. Yep, I've got a yellow data set that corresponds to our yellow model, and superimposed on that by way of these green dots are the results of the green model, which was the SimScape model. And look, your takeaway is yes, we conclude that the yellow model, which recall was our Newton derivation, is responding almost identically to the SimScape model in green. So good, as expected. All right, one more thing before we sort of ditch this model is let's go to the section called Explore Brain Reaction Forces. Let's just have a little bit of a look what's inside this subsystem. So again, I'm going to have to do the old spacebar trick just to make sure everything is displayed on screen. And we're going to have a look at some more oscilloscope plots. But this time we're going to look at Rx and Ry again. We'll also look at the magnitude, like the vector magnitude of that reaction force vector, as well as the angle of that reaction force vector. So I've tried to color code things here. When I double click on that reaction forces scope, you can kind of see the corresponding quantities. In pink, it's the time varying Rx reaction force. In green, it's the time varying Ry reaction force. And then the bottom two plots are the magnitude of the reaction vector and the angle of that reaction force vector with respect to the horizontal axis. Alrighty, so great. We've developed a model and we've simulated it, and we're able to look at the response of that model. So, folks, before we close this down, are there any questions? Are there any comments about what we've just been doing over the last sort of 40 minutes? No. Look, hopefully it's been pretty clear. All right. So look, you can close this Simulink file. Just dismiss it. We're done. And all right. And you can also close the two scripts that you probably have open right now. So these two task script files, we're done with them. You can close these script files. Alrighty, before we open sort of task 3 and 4, let me do a little bit of bookkeeping tidy up. So in our MATLAB workspace, there's a whole bunch of variables from our last two scripts. So before we start the next task, let's clean up this workspace and delete all of these things. A really, really simple way is to go to the MATLAB Home tab sheet and then look for this icon called Clear Workspace. When you click on that icon, it will scrub all of this. It will delete all of these existing variables. So please click on that Clear Workspace icon. Alrighty. So note our workspace is nice and empty, exactly how we wanted it. So big tick there. So we've done task 1, we've done task 2. Yep, you guessed it. The next file that we're going to open is this file called task 3. So let's open up task 3. So just find this file and then double click on it to open it. Alrighty. So in this task, we're going to look at a variant of the pipe pendulum. So what's changed from the original system that we analyzed is that the pendulum is now attached to another mass, the orange mass. It still has the revolute pivot point, so that revolute pivot hasn't changed. But we're going to sort of incorporate friction, such that this orange mass is free to translate in the horizontal direction. But when it does try and move, there will be a friction force exerted onto that orange mass. Yeah. So this is the revised system, right? So it's a pendulum pipe, no longer attached to mechanical ground, but instead the pendulum pipe is attached to another mass, which is allowed to slide in the horizontal direction. So we're not going to do the kinetic derivation for this system. We're going to jump straight into having a look at a model of this system. So as I scroll down the script, you can kind of see that, again, in order for us to do that simulation, we're going to need numeric values for all of the things that we're trying to represent. So look, rather than just executing this script one section at a time, let's just click on the Live Editor tab sheet and then click on the big green run triangle. And this time it will run the entire contents of our script, all of it, from top to bottom. So please click on that green run triangle. So when we do that, it defines some MATLAB workspace variables, and it opens a pre-baked Simulink file. Let's have a good hard look at that Simulink file. Hopefully some of it kind of looks familiar. So clearly we're utilizing Simscape again. So we've got our pipe pendulum, we've got our yellow rod, we've got our revolute joint. But this time you can kind of see that we've also got our orange mass, right? The orange mass is connected to our revolute joint as well. And the orange mass is also sort of free to sort of slide relative to mechanical ground. So let's kind of see, let's just see what happens. Yeah. So if you haven't done so already, go and find that green circular run button in your Simulink file and click it. Let's simulate this system and see what happens. And here it is. Here's the Mechanics Explorer again. And as I just sort of replay it, you can clearly see the sort of reaction forces exerted from the yellow rod onto that orange mass, which is resulting in the orange mass moving. And the friction that is exerted onto that orange mass ultimately brings the orange mass to a standstill. But you can just see some residual sway of the pendulum underneath it. So it's good to know that these real world effects, such as kinetic friction, can be incorporated into these Simulink models that ultimately you'll be asked to produce at some stage. If you're kind of curious as to, well, where is the block in this Simscape model that models friction, it's this one. And again, if you're kind of curious, let's double click on this guy. What I've just brought up when I've double clicked on that purple block is just the dialog parameter sort of GUI that allows me to specify values for this block. And two of those values are the coefficient of static friction and the coefficient of dynamic friction. And if you want to know even more about, how is friction represented by this contact block, then help's never too far away. Just constantly look for a question mark within the Simulink editor. And usually when you click on that question mark, it will bring up the MATLAB documentation system. And here is the Simulink help page specifically for this contact force block. And it will give you a running commentary on what it is that this block does. And more importantly, what the meaning of all of those parameters are that ultimately you've got to specify values for. Yeah. So look, if I just sort of bring up one example, coefficient of static friction. What is that? Well, you read this description and you make sure that you understand what it is that you're being asked for, and then you type in an appropriate numeric value. All right. So folks, this was one variant of the pipe pendulum. Let's look at just one more, and then I think we've done this to death. We're ready to sort of call it quits. So let me just sort of close this Simulink file, and I'm also going to close this task3 script. So the last script file that we're going to have a look at now is task4. So once you've closed out your models and closed out the task3 script, go and locate this task4 file and double click on it to open it. Alrighty. So this is what our final sort of variant of this pipe pendulum is going to look like, right? So it kind of has two fixed tines. These are these long, slender things. And you can kind of see that we've still got our concrete pipe and rod, but the concrete pipe and rod is now attached to a solid cylinder, which is going to be able to sort of slide along the two thin tines. So this is the final pipe pendulum model. So as before, look, let's just run this script from top to bottom. All right, so just click that green run triangle. And when you do, here's what the SimScape multi-body looks like for this system. We've got two tines, so two contact points, which is why we've now got two of those purple contact blocks. Yeah, one for the orange tine or prong, and one for the light blue colored prong. So yeah, look, let's run the sim and let's have a look at this final example of a concrete pipe pendulum. Just run your simulation. So a very similar result, to what we saw in the previous one, as expected. I mean, really, nothing has changed too much. We have some sort of mass. The pendulum is connected to that mass, and then you've got some sort of frictional effects between that mass and its contacts. So a very sort of similar sort of animation to the one that we visualized in task 3. Alrighty, so look, I think we're finished. I think we're finished with the pipe pendulum. Yeah. So folks, you can close some stuff down. I hope that was a nice walkthrough of how to open these files, how to interact with these files, and how to run the models. So you can close down everything that you've had open. You can clear your workspace. And I think maybe we've got a moment or two to answer some questions. Does anyone have any comments or questions that you want to ask now? Because once we're done with this session, I believe that you're going to be asked to revisit these files and open and run them yourselves. So if there's any doubt in your mind right now, now's probably a good time to ask a question. Anyone?
Yeah, please ask your questions if you have. It's a good chance to ask a question, I think. Okay, Chris has a question.
Yeah, Chris says, how do the calculations in the files differ from the calculations that we must do for the report? Look, I'll handball this over to Dongbin, but I believe, Chris, you're asked to explore systems with different parameter values. But look, let me hand this over to Dongbin.
Yeah, if you read the subject outline clearly, you can see what we are asking you to do is to establish your equations for this problem. But for this problem, suspended pipe for this one, task 3 and task 4, these two are more advanced. You want to be able to solve these two problems manually, but only using MATLAB. But for task 1 and task 2, it's possible for you to provide your manual solution, and using MATLAB, you can verify the solution you have got manually. For task 3 and task 4, you only need to use MATLAB to do analysis.
Great, thanks.
Yeah, that's fine. Yeah.
Got it. Alrighty, folks, if there are no more questions, we're going to move on to the final case study in this series. So let's do that. So let's get back to the root folder, right? So the root folder is the one where you unpack the zip file and all of these other subfolders appeared. And the folder that I'd like you to sort of go into is this one.